Hello everyone, my name is Jeff Schulz. Welcome to Extending Deep Learning to New Classes Without Retraining. I'd like to thank my co-authors, Charlie Veal, Dr. Andrew Buck, Dr. Derek Anderson, Dr. James Keller, Dr. Mihail Popescu, Dr. Grant Scott, Dr. Dominic, and Dr. Timothy Wilkin. Starting out, why would we want to extend a deep learning model to recognize n+1 classes? Well, traditional CNNs are built on closed world models. We want to be able to recognize a sample that belongs to an unknown class. The bigger question is, how can we take a machine trained for right now and extend it? How can we extend it without retraining? Is there a way, is there theory, is there math that we can implement to help this machine extend? First, we'll propose, can we build a classifier that can recognize when a class is unknown and doesn't belong to the known classes in a problem? Second, we'll look at, can we score a deep learning model with its respect to its ability to recognize the unknown class? We'll look at different metrics like, is there a separation of features in space, or do we need to project that down to make it a little easier to separate? And what are the different methods that we can project down to space, and is it even better to operate in lower space? Finally, even though this is partially funded by an ARO grant, our focus will be on benchmark data sets here for reproducible research. First, let's build our classifier that can extend to n+1. We'll start off with our data. We'll take our input images. We'll throw them into the network. This network's a little different though. We'll take off the final classification layer and take the feature vector outputs from the network. We'll then graph those in high dimensional space or project them down to lower dimensional space. And then we'll put them into the possibilistic k-nearest neighbor. Possibilistic k-nearest neighbor has our, in this case, 3 known classes. And we want to say, do new test points belong to one of these known classes, or do they fall outside of these known classes? And we should call them unknown. For test case 1, we can see that samples for known class 2 are within the bandwidth range from test case 1. So we can classify test case 1 as class 2. For test case 2, we can see that no known samples fall within the bandwidth ranges for test case 2. Therefore, we can't classify test case 2 as any of the known classes, and therefore it is unknown. Possibilistic k-nearest neighbor was introduced by Hisham Frege and Paul Gator in 2008, and it builds on the fuzzy KNN. It adds a typicality measure to its membership that can be 0. And that typicality measure can be 0 if all known samples fall outside of the class-unique bandwidths. The original pKNN bandwidths proposed were statistically derived from the data, coming at mean over 3 times the standard deviation. We found that for our data, that was much too small, and we can only assume that's because our data was much more diverse. So we decided, how can we pick the best bandwidths for each problem? We chose to implement a genetic algorithm. The cost function for that genetic algorithm is seen in the lower left, including the classification score, so we can push the genetic algorithm to classify more correctly. We also include the typicalities of the true positive, and then score against the typicalities of false positive to help increase the typicality scores within the classifications. And we also included the sum of all the bounds, with a scaling factor of alpha. This was to help influence the genetic algorithm to have smaller bounds. We found that without adding the sum of the bounds, our bandwidths got much too large and we weren't able to correctly classify unknown classes. We also introduce here, in the lower right, the typicality stem plots, which plot the typicality scores for each test class to the possible classifications. We can see that the genetic algorithm optimized ADA scored much better in our confusion matrix and showed a much higher percentage of correct typicality scores. A big question mark in our research is, what space are we operating in? Are we operating in the high dimensional space of the raw feature activations? Or do we want to project down and reduce the dimensionality to make the data a little easier to deal with? Plus, due to theories like the curse of dimensionality, operating with Euclidean distances in high dimensional space is usually not preferred. For our research, we chose to reduce our data with PCA, max pooling, and a combination of PCA and max pooling. This brings our data down from our initial feature activations, in some cases that are as high as 2048 by 7 by 7, down to a more manageable 2048 by 1 by 1. And even in cases with PCA and max pooling, we can bring down the dimensionality even more. For our second question, can we extend to n+1, or can we score our models on their ability to extend to n+1? First off, we'll start off with our known classes and our unknown classes. We know what the known classes look like in the ordered dissimilarity matrix because the model being trained on them should theoretically separate the two classes very well and have very good similarity within classes. What we don't know is how similar or dissimilar the unknown class is going to be when added to the dataset. So a model will score very well for extending to n+1 if the ordered dissimilarity matrix looks like the above. where the horse is very dissimilar to the other classes and very similar to itself. It separates well. But the model will not score very well on its ability to extend to n+1 if it looks like the below. The horse is very similar to the known classes and very dissimilar to itself. So how can we score this? We can score this with Claude. So we'll take the ordered dissimilarity matrix of our known classes, we'll throw it through Claude, and we can get a similarity score. And then we can use that similarity score relative to the context of the problem and give us a score on the model's ability to extend to n+1. We will use confusion matrices to help evaluate our performance, but it would be great if we had a more fundamental way to assess our ability to go to n+1. Claude, or clustering in ordered dissimilarity data, is a clustering algorithm meant to operate within a dissimilarity matrix. As our data is already ordered and we know its classes, we will not use the clustering ability. Claude uses two metrics to compute its clusters, a squaredness score and an edginess score. We will use a modified version and use only the squared function to compute a score of the clusters of our known classes. On the dissimilarity matrix, the squared function takes the average distance within the square to the squares around it, whereas the edginess computes the distance on the edge of the squares. We do not have a need for the edginess metric. Before we get into our experiments, let's have a look at the data we're going to be using. For our first data set, food, we have oranges and bananas from ImageNet, and we have donuts from Food 101. Our models are going to be pre-trained on ImageNet, so they should recognize features from our oranges and our bananas, and theoretically not recognize any features from our donuts. This would mean that our donuts are our n+1 class. For our second data set, we have animals. Following the same pattern, our monkeys, cheetahs, and tigers are from ImageNet, and our models are pre-trained on ImageNet. So our models should recognize features from these animals, whereas our horses are hand-picked. We did our first experiment on visually challenging classes and an imperfect data set. The imperfect data set is the Food 101, as it has increased feature and label noise. When we use no dimensional reduction on our data, and we try and put it into the pKNN, we see that we have a classification score of about 71%. With no dimensional reduction, each sample of data right now has a size of 2048 by 7 by 7, retaining both feature activations and affine transformation information. When we reduce with PCA down to 200 dimensions, we can see our performance doesn't improve much at all. It is able to slightly classify bananas and bananas as a little more, but other than that, it doesn't seem to separate our data very well. Max pooling, on the other hand, has a score of about 78. Max pooling can better separate the data, resulting in a higher classification of bananas as bananas, but we see about the same classification rate of oranges to oranges. When we combine max pooling and PCA down to a dimensionality of 180, we can see that our score improves just a little bit, and it is more likely that we can classify oranges as oranges. Though 78 to 79% leaves a little to be desired, and we can explain this with a low sample size and increased label noise in the donuts. Moving on to experiment 2, we'll be working with a little bit more relevant data, the animal data set, which should include less noise resulting in better classification. We can see that reducing our dimensionality down to about 300 with PCA, our classification is very strong within classes, but our n+1 class, horses, is misclassified as tigers. You can see in the typicality plot, though, that our horses have typicality scores for all three classes. So how can we separate that a little bit more? Max pooling does a little bit better job of separating that, resulting in a higher classification score for horses as none. You can see, though, that we're confusing horses and tigers. To us, this just means that there is potentially a better dimensionality reduction technique out there that we haven't tried. Next, let's look at scoring our dimensional reduction techniques with Claude. As a reminder, we're only computing the squaredness score of Claude. First, you can see that with no dimensional reduction and a sample feature size of about 2048 by 7 by 7, there's very little dissimilarity in the data. All the features are very similar to each other. If we reduce that data with PCA down to a dimensionality of 300, we can see that the dissimilarity within known classes does not improve, but the dissimilarity of the known classes to the unknown class is great, resulting in possibly a better classification when we reduce the dimensionality of the data down to about 300. We can see that the n+1 class pops with a high dissimilarity to the known classes, but we haven't improved the separability of the known classes to each other. When using max pooling, we can increase the dissimilarity of known classes to each other and increase the similarity of all classes, including the n+1 class, to each other. Combining both max pooling and PCA down to a dimensionality of 264, we can kind of get the best of both worlds. increasing the dissimilarity of known classes to each other, and increasing the similarity within classes. You can see that with the Claude scores on the left. Max pooling and PCA has the highest Claude score at about 0.15. Now let's score our models with Claude. Again, only computing the squaredness, we will max pool the features down and then throw them into each of these 4 models to see how they behave. An interesting story that we found out is that for the most part, Claude scores for each model improve with the number of features the model has. This isn't always the case though. DenseNet has 1900 features, but scores less than VGG at 512 features. We can see here that ResNet, with the most features, definitely performs the best. To remind you of the question we asked at the beginning, how can we take a trained machine and extend it so that it recognizes unknown classes? To try and answer that, we introduced a PKNN classifier that had the ability to say, I don't know, and we optimized its bandwidths. An issue we saw, though, is what feature space do we operate in? How can we better project down to better separate the features in space? Finding a better projection technique is something we'll focus on in the future. We also want to look at the PKNN itself. We may want to adjust or replace it, as PKNN as it exists right now assumes one shape of data. It doesn't account for data of different shapes, different topologies. Since PKNN doesn't fit the structure of every dataset, it can't be optimized for every dataset. Second, we introduced a method of scoring dimensional reduction techniques and models on their extensibility to n+1. Claude provides a relative score based on the data in the problem. Scores cannot be truly compared between different datasets, different spaces, and different models. How can we compute a global Claude score that is non-biased across all spaces, models, and datasets? And finally, we ignored half of the Claude algorithm by leaving out edginess. How can we extend edginess to work for us, or do we even need it? Can we replace it with a different metric? Improving the Claude metric on scoring dimensional reduction techniques and models on their extensibility to n+1 will be a key focus to the future of our research. Hopefully, we've given you some methods to think about when trying to extend deep learning models to new classes. Thank you.